All right, hello everyone. We are finishing up chapter 6 here with section 6.3, binomial and geometric random variables. So, learning targets for today: determine whether the conditions for a binomial setting are met, calculate and interpret probabilities involving binomial distributions, calculate the mean and standard deviation of a binomial random variable, interpret these values. When appropriate, use the normal approximation to the binomial distribution to calculate probabilities. Calculate and interpret probabilities involving geometric random variables. Calculate the mean and standard deviation of a geometric distribution and interpret these values. So, a binomial setting arises when we perform n independent trials of the same chance process and count the number of times that a particular outcome has occurred. So, the four conditions for a binomial setting are they have to be binary, which means that there's only two options. Either it's a success or a fail. All right, and they don't necessarily need to say this is a success and this is a fail, but every trial has to be able to be interpreted as either a success or a fail. Independent, the trials must be independent. That is, knowing the outcome of one trial must not tell us anything about the outcome of any other trial. The number of trials, n, of the chance process must be fixed in advance and the same probability. There's the same probability of success, which we call P, on each trial. The acronym we use to remember this is BINS. All right, so this is a little helpful way to remember binomial setting is BINS. It's also the first three letters of binomial. So bin settings, maybe. So here's a couple problems that we'll take a look at and determine if it's binomial setting or not. Genetics say that the genes children receive from their parents are independent from one child to each other. Each child of a particular set of parents has a probability of 0.25 having type O blood. Suppose these parents have 5 children. Count the number of children with type O blood. So we got independent right now, right there, and they tell us it. The success or fail. So this is it. This is where they don't state it, but you can easily find it, right? So a success would be if you have type O blood. A failure would be if you don't. So that's success or failure. There are 5 children, so the number of trials or the number of n is already known ahead of time, which is 5, and the probability is the same. It's going to be 0.25 regardless of which trial or which child you have. So there you go. Same probability, number is 5. They are independent, and the success would be type O blood. Failure would be does not have type O blood. So this is a binomial setting. B. Shuffle a standard deck of 52 playing cards. Turn over the first 10 cards one at a time. Record the number of aces you observe. So binary, yeah, you can either get an ace or don't get an ace. Those are your two options, but they're not independent. Because, for example, if the first card you turn over is an ace, then the next card is less likely to be an ace because you're not replacing the top card in the deck. If the first card isn't an ace, the second card is more likely to be an ace. So basically, the probabilities change and the independence is no longer there. So this is not a binomial setting. And here, see, shuffle a deck of cards, turn over the top card, put the card back in the deck, and shuffle again. Repeat this process until you get an ace. Count the number of cards you had to turn over. So binary, absolutely. There's an ace and don't get an ace for success and failure. Now we are independent because you've looked at it, shuffled, put it back in the card. The probability stays the same. And they are independent. Knowing the result of one doesn't change anything because they're all the same. However, the number is no longer fixed, right? It says repeat this process until you get an ace. You might do this 3 times, you might do this 5 times, you might do this 10 times. It could change every time. So the number is not fixed. So this is not a binomial setting. All right. So let's take that first example in part A, which was a binomial setting with blood type O, and we come up with the random variable x, which is a binomial random variable, and x is the number of children with type O blood. So the probability distribution of x is called a binomial distribution. And now the count of successes, which is x in a binomial setting, is a binomial random variable. The possible values for x are 0, 1, 2, ... all the way up to n. So you can have 0 children. So in this case, you can have 0 children, you can have 1 child, 2 children, 3 children, 4 children, depending on how many kids you have that have type O blood. The probability distribution of x is a binomial distribution, and any binomial distribution is completely specified by two numbers: the number of trials, n, and the chance process, uh, and the probability p of success. So number of trials and success is what determines and kind of makes this binomial probability distinct from other ones. Similar to how like a normal curve was based on the mean and standard deviation, binomial is going to be n and p. So each child of a particular set of parents has probability of 0.25 of having type O blood. Suppose these parents have 5 children. What's the probability that exactly one of the 5 children has type O blood? Don't worry about this. I don't love the layout of this slide, but think about that. You could either have, well, we'll just take a look at it. This is the formula. So let's take a look at it. Exactly one child has type O blood. So that number out in front, right? Either there's 5 different ways that could happen. Either the first kid could have it and all the others don't. The second kid can have it and nobody else does. The third kid could have it, the fourth kid could have it, or the fifth kid could have it. Those are the only 5 ways to get one child to have type O blood. Now, if one child has type O blood, that happens 0.25% of the time, and that happens once. And that means that the other 4 children don't have type O blood, which is 0.75, the probability of not having type O blood. And that happens 4 times, so 0.75 to the fourth. And like we said, these are independent trials, so you can just multiply the probabilities together, right? If 2 events are independent, probability of A times probability of A and B occurring at the same time is just probability of A times probability of B. So since they're independent, you can just multiply them together or raise them to the 4th power. So for any binomial setting, this might make a little more sense. It's the number of ways of getting that many successes in that many trials. And then it's a success probability raised to the number of successes you have times the fail probability raised to the n minus k. Now, the way to find the number of trials is actually a way called the binomial coefficient. So the number of ways to get k successes in n trials is given by this formula. Really, it's just this n over k in parentheses. Now, it's not a fraction. All right, this directly means, hey, the top number is my number of trials, k is the number of successes. So the way to get the number of different ways to get k successes is n factorial over k factorial minus n minus k times n minus k factorial. So for k is 0, 1, 2, all the way to n, and this is n factorial. So n factorial, we should be familiar with it from other classes, but n factorial is just you multiply every number, you multiply the number by every descending number. So if this is 5 factorial, it would be 5 times 4 times 3 times 2 times 1, and so forth. All right, so that's how you do a factorial. And just a caution, right? This is read as the binomial coefficient nk. It is not n over k. It's not the fraction n divided by k. It is a binomial coefficient. So here's the full formula for binomial probability. So this is like, hey, what's the probability of getting a certain number of successes in this situation? So it would be n k, which is a binomial coefficient, times the probability of success raised to how many successes you have, times the probability of failure, right? This is a binomial setting, so success and failure are complements of each other. So failure is just 1 minus b raised to n minus k. And again, where nk is just n factorial over k factorial times n minus k factorial. This number is actually also called n choose k, if you're familiar with like the choose and permutations. This is n choose k, just if you're familiar with that. We'll see that in here in a second. So when I say that the genes children receive from their parents are independent from one child to another, each child of a particular set of parents has a probability of 0.25 of having type O blood. Suppose the parent has 5 children. Let X be the number of children with type O blood. Find the probability that 3 have this value. All right. So first things first, you have to find the number of successes or the number of outcomes this can have. Now, instead of doing that whole formula 5, choose 5 factorial over 3 factorial times 5 minus 3 factorial, your calculator can just do it. So this is what I'm saying. This is choose. The way you type this in is 5, and you go over to math, and you find probability. and it's choose N, choose R. So I'm going to take 5 total, and I'm going to choose 3 of them. Then this says, hey, that happens 10 different ways. So 5, the binomial coefficient of 5, 3 is equal to 10. Now, if there's 3 successes, that means that it would be 0.25 times 0.25 times 0.25, which is 0.25 to the third. So it's going to be 10 times 0.25 raised to the third power times probability of a failure. Well, 1 minus 0.25 is 0.75. Parentheses raised to the second power. And boom, this is what it is. So there is about 8.8% probability that exactly 3 of the 5 children have type O blood. Should the parents be surprised if more than 3 other children have type O blood? Calculate an appropriate probability to support your answer. So again, X is the number of children with type O blood. It has an X binomial distribution. So this would be more than 3. That would be 4 or 5 based on the situation. So the probability that X is bigger than 3 or greater than 3 is probability that X is equal to 4 plus probability that X is equal to 5. You could do these 2 calculations in your if you wanted to, and it comes out to 0.0146. So because there's only about a 1.5% probability of having more than 3 children with type O blood, the parents would definitely be surprised if this happens, because the probability of it happening just at random is, like it says, only 1.5%. So the fact that if it did happen, it would be pretty surprising. Now, to save us some time, all right, we can compute these on the calculator without having to type in all that stuff. So the way you do it in the calculator, you're going to go to second distribution. Remember, this is where we had normal CDF and inverse norm. We're going to go to binomial. All right, and there's a PDF and CDF. So PDF, remember, is a specific value, a specific instance. CDF stands for cumulative. So you would add up all of the probabilities from less than that. All right, we do normal CDF because normal CDF is a continuous distribution, and you always have to do a range for continuous. If it is a discrete, you can do individual values. So the probability that there's exactly 3 children with it, since it's an exact number, I'm going to use PDF. And in here I put my trials, 5, comma, probability of success, comma, number of successes. And I get out that same number. So it's trials, probability of success, number of successes. Now, if I wanted to do the probability that n was bigger than 3, all right, I'm now going to use CDF. So second vars go down to binomial CDF. However, remember, CDF always goes from the left up until the cutoff point. So if I want the probability to be bigger than 3, well, that's 4 or 5. So what I'm going to do is I'm actually going to do probability of 5, or binomial CDF 5, comma, 0.25, comma, 3. Now what this is going to do, this is going to add up the probability of 0 successes, plus the probability of 1 success, plus the probability of 2 successes, plus the probability of 3 successes. That is the probability that X is less than 3, less than or equal to 3. So the probability that X is bigger than 3 would be 1 minus it. It's a complement. And that's how I get my answer. So again, in this first thing, this is adding up the probability that 0 happens, or 1 happens, or 2 happens, or 3 happens. And that's how any CDF is. It's from the left bound up until that cutoff point. So how to find your binomial probabilities if this is like a free response question. State the distribution and the values of interest. Specify a binomial distribution with a number of trials and success probability and the values of the values of the variable clearly identified. So I'm going to say, hey, X is blah, blah, blah. X equals the number of children that have type O blood. This is a binomial distribution. It's not a bad idea to define bins, like check it all. Where it says bin, like success is they have O type O blood, failures they don't. They're independent of each other. The number of trials is fixed at n, and the probability of success is the same as 0.25. Not a bad idea to state that because you get all the information in. Then you can do the calculations. and you have to show your work. You can either use the binomial probability formula, find the desired probability, which is like that parentheses 5 over 0, close parentheses, times 0.25 to the 0, times 0.75 to the 5th, and so forth. Or you could use binomial PDF and CDF, and like you did with the normal CDF, you just have to label your commands. So let's take a look. A local fast food restaurant is running a draw a 3 get it free lunch promo. After each customer orders, a touchscreen display shows the message, press here to win a free lunch. A computer program then simulates one card being drawn from the standard deck. If the chosen card is a 3, the customer's order is free. Otherwise, the customer must pay for the bill. On the first day of the promotion, 250 customers place lunch orders. Find the probability that fewer than 10 of them win a free lunch. So first, we're going to state, hey, y equals the number of customers who win a free lunch. And therefore, y is a binomial distribution because the success is you win a free lunch, failures you don't win a free lunch. They are independent. Right? The probability of one event does not, or one customer winning does not change the fact of another customer winning. They're independent. The number of trials is determined ahead of time. It's 250. That's how many people ordered lunch. And the probability of success is 4 out of 52, and it stays the same. So it is a binomial setting. So now I can go do it. I want to find, hey, the probability that y is less than 10, that is equal to the probability that y is less than or equal to 9. All right. So I'm going to use binomial CDF, and where I'm going to say, hey, this is where, same idea with like the normal CDF where you put lower bound, upper bound, mean, and standard deviation. Now you're going to do trials, probability, and x value, or you can put like number of successes also. Binomial CDF adds up 0 all the way up until that value. So this is why if I wanted less than 10, that's the same thing as probability of 0 plus 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7 plus 8 plus 9, because it is a discrete random variable. So I can do binomial CDF with all that and get out my probability. If I want to see that in the calculator, again, second vars binomial CDF 250 comma 4 divided by 52 comma 9, which is that probability. So if in fact only 9 customers want a free lunch, does this result give convincing evidence that the computer program is flawed? So after that day, 9 people won a lunch. The probability of that happening is 0.006 or less than 1% of the time. That fewer than 10 customers would win a free lunch if the computer program is working properly. Because this is such a small probability and the fact that only 9 customers won a free lunch on this day, we do have convincing evidence that the computer program is flawed. If it randomly happened, if 9 people won lunch, like that's what happened, we'd expect that to happen pretty regularly, not the probability of it happening only 0.6% of the time. Such a small probability, less than that 5% threshold. So there's definitely something fishy going on here. So the computer program must be flawed. Coming back to that type O probability, right? This is just a probability model, right? So the values of x for the binomial distribution, well, that's just 0. It's either 0 kids have it, 1 has type O, 2, 3, 4, or 5. Those are all the options. The way to, if you want to build this, right, I would just go second vars binomial PDF. Number of successes is, or number of trials is 5, comma 0.25, comma 0. Press enter, boom, 0.23. And then I'd go, hey, second vars binomial PDF 5, comma 0.25, comma 1 success now. Boom, that's my probability, and so forth to get the whole probability model if you wanted to know and kind of make this. But we can just turn those probabilities into a histogram, and we can see the shape. So this is definitely skewed right. Remember, the numbers that determine the probability model are the number of trials and the probability of a success. So, in this, like I said, the way to determine a binomial distribution is the number of trials and the probability of success. So if you kept the number of trials the same at 5, but the probability changed to 0.51, the distribution becomes a lot more symmetric. You could change it again, 5 and 0.8, now it's less skewed. All right. And this makes sense, right? Because if the probability of success happening is 0.8, that's pretty high. So the probability that it never happens or only happens once should be very small if it happens 80% of the time. You'd expect more than just one person to get out of 5 if it happens 80%. And that's kind of where our expected value is, right? Because as you can see, hey, my mean is moving from here. Let's go back. Here's the mean, right? The mean's probably somewhere between 1 and 2 here. Here it's closer to 2 to 3. And now it gets shifted back down to 3 or 4. So the way to find your mean, actually, if you know it's binomial, this is super important. It only works if it's a binomial situation. If it's binomial, the mean or the expected value is just n times p. Right? The standard deviation now, if it is a binomial situation, is the square root of n times p times 1 minus p. Just the definitions for you, but you have to be in a binomial situation here. And they'll even give you another caution. These formulas only, for mean and standard deviation, only work for binomial distributions. So assume that each of, here's another situation, assume that each of 21 students in Mr. Hawthorne's AP statistics class who did the bottled water versus tap water activity was just guessing. So there was a 1/3 chance of each student identifying the cup containing bottled water correctly. Let x equal the number of students who make a correct identification at, okay, period. At right is a histogram of the probability distribution effect. So, right, if there's 21 kids, this is probability of like 0 kids getting it right, 1, 2, 3, 4, and so forth. So you can see the largest one happened around 7, and that is still less than 2%, less than 0.2%, less than 20%. Got it correct. So calculate and interpret the mean of x. Well, it is binomial. All right. So it would just be n times p, which is 21 times 1/3, which is 7. So the interpretation is if all the students in Mr. Hawthorne's class were just guessing and repeated the activity many times, the average number of students who guessed correctly would be about 7. Right? That's the expected value. Calculate and interpret the standard deviation. Just the square root of n times p times 1 minus p. So 21 times 1/3 times, well, 1 minus 1/3 would be 2/3. Take the square root of that, which is 2.16. So if all the students in Mr. Hawthorne's class were just guessing and repeated the activity many times, the number of students who guessed correctly would typically vary about 2.16 from the mean of 7. So pretty similar to our regular mean and standard deviation definition or explanation. Now, here is an interesting fact that does actually come into play quite often from here on out. Almost all real-world sampling, such as taking an SRS from a population of interest, is done without replacement, right? Think about even when we had to explain an SRS, we had to say you will skip repeats, all right, because you don't want to sample with repeats. The problem is sampling without replacement leads to a violation of the independent condition of the binomial setting. So if you know one answer, it's going to change the others, right? You're no longer independent. However, when the population is very large and much larger than the sample size, a count of successes in an SRS of size n has an approximately binomial distribution. So it's not exactly binomial, but it's approximately, as long as our population is a lot larger than our sample size. The question is how large does that sample size have to be? Well, here you go. When taking a random sample of size n from a population of size n, we can use a binomial distribution to model the count of successes in the sample as long as the sample size is less than 10% of the population size. And we refer to this as the 10% condition. So here's the situation. In a survey of 500 US teenagers aged 14 to 18, subjects were asked a variety of questions about personal finances. One question asked whether teens had a debit card. Suppose that exactly 12% of teens aged 14 to 18 have debit cards. Let x equal the number of teens in a random sample size of 500 who have a debit card. So explain why x can be modeled by binomial distribution even though the sample was selected without replacement. So technically not independent. However, 500 is a lot less than 10% of all US teenagers aged 14 to 18. If this was 10%, that would just mean, hey, multiply this by 10. There's definitely more than 5,000 teenagers aged 14 to 18 in the US, so my sample size is big enough that I can still sample without replacement. Or sorry, my population size is big enough that my sample will be okay since it's less than 10%. All right. And now B, use a binomial distribution then to estimate the probability that 50 or fewer teens in the sample have a debit card. So X is approximately binomial because we kind of broke that independent rule, with N as being 500 and P as being 0.12. The probability that X is less than 50, that's binomial CDF. We'll do it on my calculator. Second VARS, binomial PDF. Sorry, binomial CDF. The trial is 500, comma, probability of success is 0.12, and I want 50 or less. So it's going to go, this is going to add 0 plus 1 plus 2 plus all the way up to 50. And the probability of that occurring is 0.0932. So approximately 9.32% of people, teenagers aged 14 to 18 have a debit card. We're just going to touch on this here a little bit, just so you're all aware. So don't forget about that topic. But the number of observation of N becomes larger and larger. Binomial distribution actually gets closer and closer to the normal distribution. So you can see the histogram here is the binomial situation, and then that orange line would be the normal curve. So as my probability stays the same, however, my sample size goes up, or not my sample size, the number of trials from 10 to 20 to 50 goes up, and it becomes closer and closer and closer to the normal curve, the normal distribution. So when your n is large, we can use the normal probability calculator to approximate binomial probabilities. All right. So the question again is how big. So before, your sample size had to be less than 10% of your population size. Here now, in order to use the approximately normal, you have to satisfy what we call the large counts condition. And that says that n times p, or the mean or the expected value, which we just talked about, is bigger than 10. And n times 1 minus p has to be bigger than 10. All right, so if both those things are bigger than 10, then you can approximate this probability using the normal distribution. And again, this is called the large counts because n times p is the expected value or the mean of the successes, and n times 1 minus p is the expected counts for failures. So they both have to be large enough to satisfy the normal, approximately normal distribution. So let's take over that problem where we had before, where we found, hey, about it happened 9% of the time. So why can x be used as an approximation by the normal distribution? Well, it's approximately normal, approximately binomial. With remember, this is a problem with the sample size, so it's still approximately binomial because we sampled without. However, our sample size was 500. That is less than 10% of the whole population, so we're okay there. And now n times p, 500 times 0.12 is 60. That's bigger than 10. And n times 1 minus p, which is 500 times 0.88, is 440, which also is bigger than 10. We can approximate x with the normal distribution because it satisfies the large counts condition. Now, let's do it. So we found our mean, right? The normal distribution always needs mean and standard deviation. Since this is approximately binomial, the mean is n times p, 500 times 0.12, which is 60. Standard deviation is n times p times 1 minus p, and take the square root of that, which is 7.266. Here they use the z-score table. They turn into a z-score and calculate it that way. Let's see, I'm pretty sure they did that. So we'll just use normal CDF here. Second, VARS, normal CDF. So my lower bound here is negative 1,000. My upper bound is 50. My mean is 60. Then my standard deviation is 7.266. Press enter, and here's the probability. So using the normal CDF approximation, you get 0.084. So the binomial gave us 9.3%. This gives us 8.4%. So it's really not that far off. It's a pretty good estimation, actually. So as long as your large counts conditions are kept, you can actually use a normal distribution. Now, if you know it's binomial, you might as well just use the binomial one, is how I view it. There's no reason to get fancy with it and try and use the normal CDF. It doesn't gain you any more points or anything like that. I would just go ahead and use the binomial situation if you know it's binomial. That's my personal opinion. All right. Now, one more type of random variable is called a geometric random variable. A geometric setting is very similar to a binomial with one key difference. So a geometric setting arises when we perform independent trials of the same chance process. So in the bin situation right now, we are independent, same thing, and the probability of each chance is the same. So the I and the S are there to get one success. And again, it has to be a success or failure. So the binary part is here. The only difference here is that the number of trials is not fixed. In binomial, you had 5 kids, all right? You had 500 teenagers, age 14, 18. You knew how many people you were sampling from. That's in a binomial. In a geometric situation, the number of trials is defined as it's how many it takes to get a success in the binomial setting. So, sorry, in the geometric setting. So the probability distribution of y is a geometric distribution, and it has the number of trials. You don't know how many trials there are. So it's how many until you get the correct answer. So the possible values are always going to be 1, 2, 3, and so forth. You can't get a success on the 0th trial. You need to do something to get a success. So the possible values here are 1, 2, 3, and so forth. And so the probability of a geometric distribution, finding like, hey, what if it took the 10th time or on the 10th trial it occurred? Well, that always equals 1 minus the probability raised to the k minus 1 times probability p. This formula looks a little tricky, but it's not too bad, right? So let's say the probability of success is 0.25, all right? And let's say it happens on the 10th trial. That means that the first 9 trials, it didn't happen. If the probability of success is 0.25, probability of failure is 0.75, and that has to occur on the first 9 trials. Because if it took 10 for a success to occur, that means the first 9 are failures. That would be 0.75 times 0.75 times 0.75 times 0.75, all the way up to 9 times. And then finally on the last one, the success happens, right? Times 0.25. That's all this formula is saying here. All right, so it looks a little daunting, but it's really not too bad. So let's do an example. So in class, we decided to play a game called Lucky Day Game. A student will be selected at random from your class and asked to pick a day of the week. Then your teacher will use a technology to randomly choose a day of the week as the lucky day. If the student picks the correct day, the class will only have one homework problem. If the student picks the wrong number, your teacher will select another student from the class at random and repeat the process. The game continues until the student correctly picks the lucky day. Let y equal the number of homework problems that the class receives. So basically, if you don't get on the first turn and then they don't get on the second turn, the number of students it takes to guess is how many problems you have. So if you got on the first turn, you had only one problem. If it took the fourth turn, the fourth person to get it correct, you had 4 problems that night. So that's how you get y equals the number of homework problems that the class receives. So it says find the probability that the class receives exactly 10 homework problems as a result of playing the Lucky Day game. Well, that means that on the 10th person got it correct. So that means the first 9 people got it incorrect. The probability of getting it incorrect is 6 out of 7. So 6 out of 7 to the 9th power times 1 out of 7. This is the person who finally got it correct. And that equals 0.357. All right. So B now, right? Find the probability that you get less than 10 homework problems and interpret this value. So that means that you got it before 10. So the problem here is that could happen on the first person can get it, or the second, or the third, or the fourth, or the fifth, or the sixth, or the seventh, or the eighth, or the ninth. And that could be a lot of calculations, right? Because the probability that it happens on the first one would be 1/7. Probably having on the second would be, hey, the first person got it wrong, which is 6 out of 7, times not getting it right. And then probably the third person gets it right is the first person gets it wrong times the first person gets it wrong, the second person gets it wrong times the third person gets it right. And you have to do that for all of these. If you did that, it would come out to about 0.7503 or 75%. So there's about a 75% chance or 75% probability that the class will get fewer than 5 homework problems by playing the Lucky Duck game, the Lucky Day game. Sorry. Now, I'm not going to make you do that. The calculator will actually calculate it for you. So just like the binomial situation, there is a geometric distribution. The second vars go down binomial, binomial, geometric, PDF, and CDF. Same idea, right? PDF is the number of attempts it takes to happen. So I'm going to do my probability, which is 1 divided by 7. And I want that to happen on the 10th trial, right? The 10th person gets it. So that'd be 10. And boom, 0.0356. So this is, if the probability of success is 1/7, the probability of the 10th person getting the first success is 0.0357. PDF, on the other hand, same idea. Or sorry, CDF, on the other hand, does the same idea. Probability that X is less than 10, that's the same thing as saying, hey, probability that X, it either happened on the first, or the second, or the third, or the fourth, or the fifth, or the sixth, or the seventh, or the eighth, or the ninth, or the 10th. All right, to do that, you go second, distribution, go all the way down by geometric, CDF, all right, 1 divided by 7, comma, how many now? It's 9. If I want to include 9, press enter, boom, 0.75, or about 75% of the time. All right. So same idea here. You could do this, right? You could do binomial PDF for 1, 2, 3, and so forth. These are the probabilities that you would get. They just turned into a histogram from here now. So any geometric distribution, it's always going to be skewed right. And that makes sense because at best, right, let's say you start off 0.25 is a success. That means the probability that the first person got it right is 0.25. If you take the second person, right, it's going to be 0.25 times, well, the first person got it wrong, so it'd be times 0.75. I'm multiplying decimals, I'm automatically going to get smaller and smaller, right? If it took the third person, it would be this times 0.75, and so forth. It would just get smaller and smaller and smaller. So every geometric distribution has a right skewed shape. Binomials could be left skewed, right skewed, or symmetric, depending on its mean and the number of trials, but geometry is always skewed, right? The center of the expected value here is 7. We'll take a look at how do you actually find that. And the variability is 6.48. So how did I get these numbers? Well, the expected value for a geometric distribution is always 1 over p. The probability of success was 1/7. So the expected value is 1 over 1/7, which is just 7. And then the standard deviation is here. So if I wanted to calculate this, it'd be 1 minus 1/7 divided by 1 divided by 7. And then square root 6, 2.44. What did I do wrong here? What's that? Double check on my own calculator. Interesting. I think I might have had it wrong on the first problem here. This is the formula, just so we're all clear. So, we have a new situation, or we're going back to that draw 3. So this is a slightly different one. Now, before it was like the number of people who won the lunch, a free lunch that day. Now we're going to let X equal the number of customers it takes to get the first free order on a given day. So we're seeing how long it took for the first person to be free. So the mean, well, remember it happened, the probability of a success is 4 out of 52, right? So the mu is just going to be 1 divided by 4 divided by 52, which is 13. So we'd expect it to take about 13 people to get the first win of the day. So if the restaurant runs this lunch promotion on many days, the average number of customers it takes to get the first free order would be about 13. And then calculate and interpret the standard deviation. Well, same thing here, it's going to be 1 minus 4 divided by 52. I see what I was doing wrong. In this problem here, I should have done, 1 minus 1/7. Take the square root of that answer. And now divide by 1/7. And that's how you got your standard deviation from before. So I made that mistake. It's not the standard deviation of the whole thing. It's just standard deviation in the numerator. So 1 minus, 4 divided by 52. Take the square root of that. And then divide by 4 divided by 52. Boom, 12.49. And to interpret that now, if the restaurant runs this lunch promotion on many days, the number of customers it takes to get the first order would typically vary by about 12.5 from the mean of 13. And there you have it. That is the end of chapter 6 for us, people. Enjoy.